effect of firing angle error. So, for the sake of explanation, I will take a simpler case, a 6 pulse LCC, line commutated converter. So, the circuit I am considering is this. So, this is a 6 pulse LCC. I will consider the DC side to be represented by a current source ID, which is constant, and the AC side, for the sake of simplicity, represented by a 3 phase balanced voltage source. Now, when I say firing angle errors, there are 6 thyristor valves, valves 1, 3, 5, 4, 6, 2. So, there can be firing angle errors for all the thyristor valves. Now, suppose there is an error in all the thyristor valves firing angle. That means I am supposed to give a firing angle or a gate pulse at some instant, it gets delayed. Now, if it gets delayed by the same amount for all the 6 valves, will it lead to non-characteristic harmonics? It is only firing angle error, but it will not lead to non-characteristic harmonics. Okay. See, the point is, if I delay the firing angle by the same amount for all the 6 thyristor valves, it is actually saying I am changing alpha, that is all. So, it is error, but it will not lead to non-characteristic. No, so what can I do is, I can assume that one of the firing angle errors is 0, that means for one thyristor valve. So, there is no loss of generality. In assuming that the firing angle error for one of the valves is 0. So, firing angle error. So, one of the valves means I take say valve 1, firing angle error for valve 1 is 0. Okay. So, that means there are firing angle errors for the other thyristor valves. Say, let the error in firing angle. So, I will consider an example where there is only delay, that means there is no advance. So, the firing angle error means here the gate pulse is delayed. See, I can also consider error in the form of an advance of the gate pulse. The gate pulse is coming before it is actually required. Okay. So, the error in the firing angle, which is a delay for valves 2, 3, 4, 5 and 6 B. So, I denote this firing angle error by epsilon 2, epsilon 3, epsilon 4, epsilon 5, epsilon 6 respectively. Okay. So, let me take one example. So, there are many possible ways of getting this firing angle errors. Let me take an example. So, in this example, epsilon 3 and epsilon 5 are say 0, and epsilon 2, epsilon 4 and epsilon 6 are equal, and since they are equal, I will use a common notation epsilon. This is just one example. Okay. Now, let us see what is the effect of this firing angle error on the harmonic components of the AC side current. See, there is an AC side current here. So, in phase A I have IA, in phase B I have IB, in phase C I have IC. So, we know ideally what are the harmonic harmonic orders in these currents IA, IB, IC. They are of order 5, 7, 11, 13, 17, 19, so on. Okay. So, we will see whether this will result in any harmonics other than these characteristic orders. So, for that what I will do is I will try to plot the currents. I will plot one of the currents. See, one can verify that the currents IA, IB, IC for this case can be identical. I will plot one of the currents, say IC. Now, what I will do is I will use a notation ICO for ideal IC. So, this is the ideal current in phase C. And due to firing angle error, the current in phase C is IC, which is nothing but ICO plus some error. I will call that error as delta IC or the deviation in IC. So, I will plot first the ideal current ICO, then I will plot IC due to firing angle error. Now, if you look, okay, let me come back to this circuit. For this circuit, are the harmonic component magnitudes dependent on alpha? If I take the AC side current harmonics, are they dependent on alpha? Huh? Are they dependent on alpha? It is independent of alpha. For this circuit, it's the AC side harmonics, current harmonics are independent of alpha. Okay. So, without loss of generality, I can fix some value of alpha. It's independent of alpha, in fact. Okay. So, let alpha be 0. Let alpha be 0. So, let me take the plot of ICO, which is the ideal current. So, I am marking every 60 degrees. So, suppose the first step I have shown here is the instant at which say valve 6 is turned on, then valve 1 is turned on at this instant, then 2, 3, 4, 5 and again 6, again 1. Okay. So, I have not marked any numbers on the omega OT axis, but instead I have shown the instants at which the valves are turned on. Okay. Now, between these two instants, that is the instant at which valve 6 is turned on and the instant at which valve 1 is turned on, what is the value of ICO, the ideal current? I am not marking, I mean I think it should not be difficult to answer. See, when 6 is turned on, which two valves conduct? 5 and 6. 5 and 6. When 5 and 6 are conducting, what is ICO? Minus ID? Plus ID. It is plus ID. It's plus ID. Okay. So, between, so I will use a different color. For ICOs, let me take ICO, of course. For IC, I will use. Okay. So, plus ID. Now, as soon as valve 1 is turned on, what happens to IC? 0. So, it goes to 0 and it remains at 0 till valve 2 is turned on. Now, what happens when valve 2 is turned on? What happens to ICO? Minus ID. So, it goes to minus ID and remains at minus ID for how many degrees? 120 degrees. So, till valve 4 is turned on. Then again it goes to 0. Then when valve 5 is turned on, it goes to plus ID and it remains at plus ID for 120 degrees. Okay. So, this is the ideal waveform. So, it is either equal to ID or minus ID or 0. Fine. Now, let us come to the actual IC, which is the waveform when there is firing angle error. So, what is the firing angle error? The firing angle error is only in valve 2 and valve 4 and valve 6. So, all these valves 2, 4 and 6 which form the lower commutation group, there is a delay of epsilon in the firing angle. Okay. So, due to that, I made a mistake. This is ICO. Let me use a different. This is ICO. Okay. So, there is no error in valve 1. Of course, valve 1 we have said without loss of generality error is 0, and there is no error in valve 3 firing and valve 5 firing. So, there is only error in 2, 4, 6. So, does the error in the firing angle of valve 6 affect IC? It will not affect. So, if I plot IC, it will not affect. I can still have the same waveform from the instant of turning on valve 6 and to the instant of turning on valve 1. Now, there is no firing angle for valve 1, so it remains as it is. What about the firing angle error in valve 2, due to which the valve 2 is turned on at a later instant? So, there is a delay. So, there is a delay. Then there is an error in the firing angle of 4. So, due to which it does not go to 0 as in the case of the ideal condition, it goes to 0 at a later instant. Then it remains at 0 for less than 60 degrees. Then there is no error in the firing angle of valve 5. Then the firing angle error in valve 6 has no effect on IC. Again, valve 1 there is no error. Okay. So, there are two deviations in one cycle. Say if I take turning on of valve 1 and the next turning on of valve 1, it completes one cycle. Okay. So, there is an epsilon width which is an error here. Similarly, this width is also epsilon. Now, I said alpha is 0, which is without loss of generality. That means the instant of alpha is the instant of turning on of valve 3. So, our EA, EB, EC, the three voltages on the AC side are defined in such a way that the instant of turning on of valve 3 is alpha. So, that means this is the instant omega OT equal to 0, the instant at which valve 3 is turned on, which I have chosen to be 0. So, this is 0. Okay. Now, if I look at IC, IC is given by the ideal ICO plus a deviation delta IC. Let us look at delta IC. So, if I just want to know what is delta IC in one cycle, so the deviation from the ideal case is only at two places, due to the firing angle error in valve 2, due to firing angle error in valve 4. So, it is what is the deviation due to firing angle error in valve 2, delta IC is non-zero, and what is the value ID from for what values of omega OT minus minus pi by 3 or 60 degrees to So, omega OT greater than minus 60 degrees and less than minus 60 degrees plus epsilon. And there is one more error due to firing angle delay in valve 4. So, that will result in delta IC equal to minus ID, and this is from 60 degrees to 60 degree plus epsilon. Now, why I am interested in delta IC is, I am interested only in the non-characteristic harmonic. I am not interested in the characteristic harmonics. So, if there is some non-characteristic harmonics, it will be there in delta IC. Okay, that is the idea. So, what I am trying to say is, if H is the order of a non-characteristic harmonic, then the RMS value of Hth order harmonic component in IC is equal to the RMS value of Hth order component in what? Delta IC. So, if I find a harmonic component in delta IC, it is nothing but a non-characteristic harmonic component in IC. That is what I want. So, instead of trying to find the harmonic component in the current IC, I find the harmonic component in delta IC, because I am only interested in the non-characteristic harmonic now. Is that okay? Is that okay? Yes or no? Yeah. Where? Okay, okay, let me make a few points more clear. So what I have shown here, delta IC, the expression, first of all, I have said wherever it is non-zero. So it means it takes a value 0 otherwise. Okay, that is one thing. So this gives the expression for delta IC in one cycle. Your question is why I have taken 0 at the instant of turning on valve 3. So I said without loss of generality, alpha is 0. Alpha corresponds to instant of turning on of valve 3. Yes. Harmonic? They are not same. So if I take any characteristic harmonic, IC and delta IC will not have the same values of characteristic harmonics. Now my intention right now is to show that there is some non-characteristic harmonic. So if there is a harmonic in delta IC, it means it is a non-characteristic harmonic. So it might also have it may also have, yeah, what I am trying to show is it will have non-characteristic. So instead of showing it in IC, can I show it in delta IC?
Yes, it will have non-characteristic, but not only non-characteristic.
Okay, okay, my intention is to show that there is some non-characteristic harmonic. Okay, so if I show it in delta IC, is it sufficient is the question?
Yes.
It is sufficient to show it in delta IC.
Yes.
Instead of taking the actual current, I am taking the deviation, that's all. Okay. So let us try to see what happens to the harmonic component in delta IC. Okay. So go to the next. So I know the expression for delta IC I have given here. It's either equal to ID, R minus ID, or 0, and it is equal to ID for a small duration epsilon, and it minus ID for a small duration epsilon. Okay. So the RMS value of Hth order harmonic component in delta IC, suppose I use this notation IH. Suppose I use Fourier series, I can write this as, if I use the exponential form of Fourier series, it is CH, where CH is complex. So root 2 times absolute value of CH. So if, see, I can as well write it in terms of the trigonometric form coefficients AH and BH also. So it is root 2 by 2 pi into, so if you look at the definition of CH, it is 1 by 2 pi into integral over one cycle. Okay. So here from minus 60 to minus 60 plus epsilon, I have a non-zero value, that is ID. Exponential of minus j h omega ot d omega ot, and there is one more duration for which it is equal to minus ID. So plus integral 60 to 60 plus epsilon. So here it is minus ID, exponential minus j h omega ot d omega ot. So one can actually try to simplify this. I will not do the simplification, but I will try to give the final expression which we obtain after all manipulations. I will leave it to you to show that this is equal to 2 root 2 ID by pi h into absolute value of sine h epsilon by 2 into sine 60 degree into h. So this is the expression that we get after integrating and doing all trigonometric manipulations, conversion from exponential of the complex number to sine and cos and such things. So this I will leave it to you to show. So please derive this. Yes. No, it's a degree. So since I have written 60 degree, h is just an integer. H is just an integer. Okay, so it is 60. Yeah. Huh? Sorry. Yeah, sine. So whether h epsilon is in degree or radian depends on whether epsilon is in degree or radian. That's all. So I have not said anything about that. You take in degree or here the other factor I have said 60 degree means 60 degree into h is also in degree. Of course. Yeah. So I am only looking for non-characteristic. So my goal here is to show that I get some non-characteristic. That's my only goal. See, if we get again characteristic, that we already know. We know some characteristic harmonics are there. Non-characteristic harmonics are present. I mean, the presence of non-characteristic harmonics have to be proved here. That's what I am trying to do. That's all. By that way of taking an example. Okay. So, can h take any non-characteristic value is the question. Is there any value of h for which this is 0, first of all? Yeah. 3, 6, 9, all multiples of 3 it is 0. Okay. So, one possibility is 0 if h is a multiple of 3. Right. Now, suppose h is not a multiple of 3. H is not a multiple of 3, and if I want only non-characteristic harmonics, h should be, see, please note I am not, see, this will not give characteristic harmonics in IC. If I want characteristic harmonics in IC, I have to take IC only, I can't take delta IC. Please note that point. If I want characteristic harmonics, what is the effect on characteristic harmonics? I can't take delta IC, I should take IC. Okay. Now, to show the presence of non-characteristic harmonics, what I am doing is I am taking delta IC. So, non-characteristic means h is not a multiple of 3 and h is even. H is even. Yeah. Is that okay? See, if h is odd and not a multiple of 3, then it is not non-characteristic, it is characteristic. Then all this analysis becomes meaningless. See, please go back to this sentence. If h is the order of a non-characteristic harmonic, only then doing harmonic analysis of delta IC makes sense. Otherwise, I have to do harmonic analysis of IC only. Okay. So, if h is not a multiple of 3 and h is even, what is the expression? What is sine 60 degree into h? You take any h which is a multiple of, which is not a multiple of 3 and which is also even. So, absolute value means root 3 by 2. Okay. So, sine 60 degree into h is root 3 by 2. So, I get root 3 by 2 means root 6 id by pi h into absolute value of sine h epsilon by 2. So, this is the expression if h is not a multiple of 3 and h is even. Now, this one will be non-zero as long as sine h epsilon by 2 is non-zero. So, there is a possibility of h taking values such as 2. Can h take a value of 2 and the sine h epsilon by 2 is still non-zero? Suppose h is 2, then this absolute value is sine epsilon, absolute value of sine epsilon. So, it can still be non-zero for some value of epsilon. So, there is a possibility of a non-characteristic harmonic. So, 2 is a non-characteristic harmonic. Similarly, 4. Okay. So, this example just shows that one can have non-characteristic harmonics by firing angle errors. So, that is the idea. Okay. So, if I want to I mean, eliminate non-characteristic harmonics only way is by ensuring that there are no firing angle errors. And I have symmetry in the two transformers. I mean, the parameters are almost identical, but that comes by design only. And the operation also, there should be no imbalance in the operation of the two bridges. So that way one can avoid the non-characteristic harmonics. So characteristic harmonics are always there, and we have seen how to eliminate by using only 12 pulse, but that will not be sufficient. We still have in the 12 pulse converter 11th order harmonic, 13th order, which can be, I mean, a significant harmonic component. Ideally, we want sinusoidal current to be drawn from the AC system. So how can we achieve that objective of going towards or tending towards sinusoidal waveform? Using a 12 pulse, of course. What we do is we use a filter. So one can use a filter to reduce the harmonic component drastically, so that the current drawn from the AC system is almost sinusoidal. So we will look at the filters in the next class, but why do we need filters? Why not? I mean, if harmonics are there, what is the problem? What is the problem? If there is, leave the harmonic, let it be there. Don't use filter, let it be there. 12 pulse LCC is there, the harmonics are 11, 13, 23, 25 and so on. So these harmonics are there, let it be there. What is the problem?
Power factor.
Power factor. How is harmonic related to power? Yeah, you are talking about, yeah, that is one thing. Anything else?
And then
No, say, think of some tangible effect. See, power factor is again abstract. Say, okay, one then ask the question, okay, let it be, let the power factor be low. See, I can only understand things like, okay, I have to pay for it.
if power factor is low, I have to pay for more power.
That means where do you pay? I mean, huh? Losses, yeah, there will be more losses. So, see, losses is not only causing additional power to be lost. Whenever there is loss is in the form of heat, and heat means you have to make additional expenditure to cool. I mean, cooling arrangements have to be made. Wherever there is loss, I mean, in excess of what is actually expected, you have to make cooling arrangements. It's not just power is lost. You have to make additional cooling arrangement for that. And there are a few other problems. I mean, we will look at these problems with harmonics, due to which we have to use filters. Okay, so we will discuss about that in the next class.